Okay, so what we're looking at today is something called combinations. And so, I put up here counting techniques, calculating combinations, or groupings of objects where order doesn't matter. So, what we're going to see today is something really important about the difference between a combination and a permutation. Now, just to start it off here, you can see we've got the big scary combination monster, and then big scary permutation monster. And the formulas for each are listed below. Now, we already know the big scary permutation formula, which is right here. And this is where order matters. So arrangements where the order matters. Okay? The exclamation mark is not a factorial. And over here, we're going to find out that there's an extra little r factorial written here, which is the number of objects that you're selecting. And here we'll say we're going to find out that order does not matter. So it's groupings of objects where order doesn't matter. Okay, so the difference between the two of them. And then we'll wrap up the organized counting techniques. So how does this work? Well, first of all, you might want to highlight this bit up here. Permutations are arrangements of objects in which the order of the items matters. Combinations are the arrangements in which the order does not matter. So that's a key point. All right, so let's look at a situation where we have distinct tiles. So these tiles are red, blue, white, and green. And we want to calculate the number of permutations if we're selecting 3. So imagine that we have these 4 tiles, and I say how many ways can I grab them where the order matters. So the very specific ordering matters. So I could pick red, blue, white, red, blue, green, blue, white, green, or green, white, blue, green, blue, red. The order would matter. Well, you would first of all say, well, how many options do we have for the first spot? Well, there's 4 distinct times 3 times 2 times 1, which is 24. Or you could say, well, it's just 4 P3. I have 4 objects and I want to take them 3 at a time. Another way of writing that, like this, or it's 4 factorial over 4 subtract 3 is 1 factorial. There we go. Okay, so it's the same thing. It's fundamental counting principle, or you can use the permutation notation method. All right, now let's list all of the permutations of these. So for example, let's start with red, blue, white. So I could grab red, blue, and white, but I could have also grabbed it as red, white, and blue. I could have also grabbed it as blue, red, and white, blue, white, and red, white, red, blue, white, blue, red. Or I could have gone red, blue, green, red, green, blue, blue, red, green, blue, green, red, green, blue, red. If you want to do this on your own, you totally can. I'm just going through them quickly here. And I just start with, if I start with green, I could go white and then blue. If I start with green, I could go blue, then white to switch the order of those two. I could move the white over here and go green, blue, and then I can leave the white and go blue, green. So you just see what all I'm doing is switching the order of which one starts and then switching the other two. Okay? I could go red, white, green, and you can do this on your own and then just double check that you got what I get when I do it. Okay, green, white, red, green, red, white. Okay, now here's the thing. If you look at this, right, it says how many distinct groupings are there where we ignore the order? Well, you'll see that this first set here, all of these here are the same objects, just in different orders. This next one here has all of these are the same colored objects in different orders. This next one has these ones there, and the last one has this. So what you'll notice is that there are 4 groups of 6. Okay? So there's 4 distinct groups of 6 arrangements. Okay? Of 6 arrangements. Now, 6 arrangements because it's 3 factorial arrangements, and then you would times it by 4, and that's where that 4 factorial comes from. There's 4 groups of 3 factorial arrangements of the objects. So there's only 4 distinct groups, and they are red, blue, and white in any order, blue, red, and green in any order, green, white, and blue in any order, or white, red, and green tiles in any order. And so since there's only 4 and it says list each of the combinations, so take these things that you just wrote here and they go here. Okay, that's where they should be. That's where the 4 of them go. Now, how can we calculate it? Well, it turns out it's quite easy. What you would start out with is you would look at it and say, well, how many permutations are there? Well, if there's 4 objects and I'm taking 3 of them at a time, that's perfect. And then say the number of permutations. So how many ways are there of rearranging the 3 objects? So basically we look and we say, well, there's 4 ways, 4p3 ways of arranging. There's 24 total ways of arranging these objects, taking them 3 at a time. But each of those objects, since there's 3 objects, there are 3 factorial ways of arranging them. And what you'll notice is 4p3 is really 4 factorial over 4 minus 3 factorial, but there's this 3 factorial sitting right there. There's that 3 factorial right there. And there it is. So this is the permutation situation, and down here is the number of objects that we chose. And so that's 24 over 6, because that's 1 factorial times 3 factorial, which is just 6, and we get 4 is our answer, the number of distinct groups where order doesn't matter. Another way of looking at this 4 factorial over 4 minus 1 was really n factorial over n minus r factorial, because it said we had n objects and we're taking 3 of them, and then there's the ways of arranging those distinct objects. So that's an r factorial, like that. So it's n factorial over r factorial times n minus r factorial is the number of combinations. So we write it as NCR for number of combinations. Okay, so another way of thinking about it is that if you want to figure how many permutations there are, you say, well, how many groups are there? Well, there's 4 distinct groups. And how many ways of arranging each of the objects in that group? Well, there's 3 objects in this group, so it's 3 factorial ways of arranging these. So 3 factorial times 4, because there's 4 groups. Well, what do you know? That becomes 4 times 3 times 2 times 1. Which is, sorry, we didn't times it by 1. 4 times 3 times 2. So go back and fix that. You're not multiplying by 1, because we're only taking 3 of the objects. And you basically will end up with the exact same thing, where you'll get the 4p3 or 4 factorial, because 4 times 3 factorial is 4 factorial, which turns out to be correct. So they are connected and intricately connected. All right, so what is a combination? Well, a combination is n distinct objects taken r at a time, and the selection of the r of the n objects without regards to order. The total number of combinations of objects taken r at a time is denoted by n choose r, or NCR. And so we read it as n choose r. N choose r, or n choose r. NCR is another way of thinking about it. On your calculator, it's NCR. So I put here's an alternate explanation. Calculate the number of combinations of r out of n objects. So in order to find the number of arrangements, you must arrange the r objects. There are r factorial ways of doing this. So another way of thinking about it is say, how many combinations of the objects are there? And then multiply it by how many arrangements of those objects there are. What you'll result in is that the combination formula will be n choose r is equal to Pn comma r over r factorial. And so we get the formula that we had on the previous page. So n choose r can be done as n choose r, and sometimes you might see it as n comma r, but this is almost never used. Almost always it's n choose r or ncr, like that. All right, let's do a quick example and see how we do with this. Let's say you have 10 books that you want to place on your shelf, and you only have space for 8 of them. Okay? How many ways can you place the books on the shelf if the order absolutely matters? So if the order matters in this case, what do? Well, we have 10 spaces, 8 spaces, so 1, 2, 3, 4, 5, 6, 7, 8. And there's 10 books, so there's 10 choices for the first one, times 9, times 8, times 7, times 6, times 5, times 4, times 3, and that's it. Okay, so that's how many there are. That's using the fundamental counting principle. So another way of doing that, and that comes out to a big number, like that. So that's using the fundamental counting principle. Okay, another way is just say there's 10 objects. How can we arrange 8 of them? And it's 10 factorial over 10 minus 8 factorial, which reduces down to this because the 2 factorial divides out. And if you put it in a calculator, you get the exact same thing that you get using the fundamental counting principle. Okay, what about if the order doesn't matter? Well, if I have 10 objects and I just want to choose 8 of them, we say that's 10 choose 8, so either notation is fine. And that's 10 factorial over 8 factorial, 10 minus 8 factorial. Or you can write 10 factorial, 10 minus 8 factorial times 8 factorial, doesn't matter, it's the same difference. So basically what you're doing is you're taking the exact number you had before, the number of permutations, so there were 1,814,400 permutations, and say, well, I don't care what order those 8 objects are in. So we divide by the 8 factorial arrangements of those objects. And it turns out there's only 45 ways of grabbing 8 books out of the 10 that you have and putting them on a shelf where you don't really care about the order. You just care that you selected 8 books. But there are still 45 different combinations of books that you could have. All right, so on your calculator it says use your NCR button to calculate the number of combinations. So again, this is the same thing as saying 40p7 divided by 7 factorial is another way of thinking about it. And it's 18,643,560. 30 choose 5. If you put it in your calculator, try it first. Should get you about that number there, or exactly that number there. Okay. In the last example, actually we'll do a couple more. Let's say there's 31 people in your data management class. How many ways can you choose a group of 5 people to represent the class at a school-wide assembly? Now, the order doesn't matter. You don't care. It's not. These aren't presidents and vice presidents. We're not assigning a role to these 5 people. So the order doesn't matter, and that's so important. Order doesn't matter. We just want to send 5 students down to the gym for this assembly. So we would say, well, in that case, we're talking about a combination. 31 choose 5 or 31 C5. And that is 169,911 ways. You could have thought about it as saying, well, it's 31 P5, how many different arrangements of those people are there, and then divide it by 5 factorial. And you'll get the exact same answer, right? There's nothing different about it. Because what that tells you is that if you wanted to assign an order to those 5 people that you picked out of the 31, but then say, hey, after I've got those 5 people, really, I don't care about the order. So there's far fewer combinations. So almost always, NCR, the number of combinations, is less than the number of permutations by a factor of R factorial. Okay? So the number of combinations is always less than the number of permutations by a factor of the arrangement of the objects that you selected. and that's r factorial. Okay. Let's say that you go to Sweet Molly's and you got to buy some candy. The store is low on stock and only has 8 kinds of chocolate and 11 kinds of candies. Okay? You want to buy 9 things, consisting of 4 chocolates and 3 candies. Okay, so the word and is being used here. So as soon as you see the word and, you should start thinking about multiplying. Okay, so how many ways can the chocolates be chosen? Well, we know that there's 8 kinds of chocolate, and we want to choose, because I don't care what order I get the chocolate in, there's 8 kinds of chocolate and I'm picking just 4 of them. So that's 8, choose 4. 8 minus 4 is 4 factorial. The objects, I'm arranging 4 factorial items, so there's 70 total combinations of chocolates I could pick. And this is clearly 7, not 9. Makes no sense, because 4 plus 3 is 7, not 9. The candies can be chosen in, there's 11 candies, I'm only choosing 3 of them. 11 minus 3 is 8 factorial, and then there's 3 factorial ways of arranging those objects once you grab them. So it's 165 in total. So the fundamental counting principle says that there are 8 choose 4 times 11 choose 3, which is 70 times 165, which is 11,550 combinations of chocolate, or 4 chocolates and 3 candies that you can pick. So one neat thing about this is that 8 and 11, the top is going to tell you the total number of objects that you're selecting, and the bottom will tell you how many of the objects when you add them up in total. So there's 7 that we picked, and there were 19 in total to pick from, and how many we're picking of each. That's super important to think about. What the top adds to and what the bottom adds to will match what your question asks. You want to buy 5 different chocolates and 6 different candies. Sorry, or, so and, we know multiply, or we know we're going to add. Okay, so again, maybe key points here. Okay. All right, 5 different chocolates. So we have 8 chocolates to pick from. We're going to pick 5. Plus 11 candies, we're picking 6. So it's 56 plus 462. So there's 518 combinations. Now here's a neat thing. Like, let's say that you were going to pick all 8 chocolate and all 11 candies, right? In that type of situation, you'd say, well, how many ways are there to pick all 8 chocolates and all 11 candies? Well, there's only one way. And if you thought about it, that would be 8 choose 8 times 11 choose 11. 8 choose 8 is just 1. 11 choose 11 is just 1. So 1 times 1 is 1. So there's only one way to take all the chocolate bars and all the candies. If order mattered, then it would be a little bit different, because we could grab them and then we could arrange 19 factorial ways of arranging those items, which is a huge number, right? So the difference between combination and permutation is quite important. All right, so you're going to practice this on your own, but I'll get you started on it. So say you have a club that has 25 people. And how many ways can the committee of 3 members be chosen? Now when it says a committee, order matters. So now the tricky part of this course comes in, where you're thinking about order mattering or not mattering. In how many ways order, in this case, does not matter? Okay. In how many ways can the committee, because it's just a committee, right? There's 3 members being picked. They don't have specific roles. We're just saying, hey, grab 3 people out of 25. So that's 25, choose 3, which is 25, C3. There's about 2,300 different groupings of people you can make where there's 3 people in it of the 25 people in that club. In the next one, it says, how many ways can you fill the office of president, secretary, and treasurer? In this one, of course, order matters. Fundamental counting principle says that's going to be, there's 25 positions for the first person, then there's 24 people left to pick from, 23 left for the last one. And that's a big number, 13,800 different arrangements. Or you could just say it's 25 and we're picking 3 of them. 13,800. Same answer. Okay, let's say that we have Acton High School's improv team consists of 5 boys and 5 girls. How many working groups of 4 people can be formed with no restrictions? All right, so we're just picking groups. Doesn't matter. There's no restrictions whatsoever. So in this case here, we would say, well, there are 10 people in total, and we just have to pick 4 of them. But I don't care about the order that I'm picking them in. So that's going to be 10 factorial. 10 minus 4 is 6 factorial. That's 4 factorial. Or just use the calculator, and you get 210. Okay. Ooh, what if it has to have 4 boys on the team? Or 4 boys in the group. Well, there's only 5 boys to pick from, so we're going to have to pick 4 of them. How many groups of 4 boys are there? Well, it's 5 choose 4. Okay, and that's for the boys. And then the girls are next. And for the girls, it's 5 choose 0. Because there are no girls going to be on it. Well, 5 choose 4 is just, there's 5 ways of picking 4 boys from the group. And the ways, if there are 5 girls and you're picking none of them, there's only one way that can happen. 5 choose 0 is always just 1. So there's only 5 ways of doing that. Now notice, 5 plus 5 is 10, 4 plus 0 is 4, so we still get the 10 choose 4, or the 10 and 4 adding up properly. Remember, these and these numbers match the original question. If they don't, you should rethink what you've done in that question. Okay, in this next one, it says that there are 3 boys and a girl. Okay, well, there are 5 boys. We're picking 3 or choosing 3, and there are 5 girls, and we're choosing 1. 5 and 5 is 10. 3 and 1 is 4. So we're still picking 4 people for this group. 5 choose 3 is there's 10 arrangements, and 5 choose 1. Well, how many ways? If you have 5 objects, how many ways can you choose one of them? Well, you can just pick each one of them separately, so that's 5 ways, and that comes out to 50. All right. So what you're going to do from this point is you're going to try and finish off these questions. And then we will take them up in class and see how you did on them.